How's everyone doing? Morning. We recovered from the community party? Everybody? Good. So, real quick housekeeping first. There is another schedule change today. It is posted a few different places on all the walls. It's not reflected here, but it is on the app and it's on the projection. So please just take a look at that. There's a few swaps. Additionally, after the conference, all the talks are over, there will be a Q&A with the Scala team. We always end with that. So if you want to come here and ask them really, really hard and personal questions, feel free. It's a good time. So with that, I'd like to introduce Adam Gibson. He is the co-founder of Skymind. And in some fun news about Adam, we actually dropped the last letter of his framework because it was J for Java. So on the thing, it's actually called Deep Learning for J.
It's Deep Learning for S. It's Scala. It's fine.
For S. Okay.
Yeah.
Deep Learning for S now. Yeah.
Yep.
So we're going to change it. Adam is a co-founder and a big AI guy. So we want to welcome him.
All right. Thanks. All right, so out of curiosity, how many of you guys actually came here for big data, machine learning? Most of you guys like software engineers. I see how this is. Okay. All right, so what I'm actually going to talk about today is more of an engineering-oriented take on artificial intelligence and relating this actually back to Scala. A lot of this actually is going to be about software architecture of machine learning systems and what they'll look like on the JVM in the next 5 to 10 years, and some extra things to think about in terms of scale. So first of all, what is artificial intelligence? So artificial intelligence is not Terminator. We are nowhere near general artificial intelligence. If you guys have ever heard about robots killing us, Elon Musk and all that, no. We can do basic pattern recognition at best, nowhere near close to the hype. Yes, we can recognize like how many people are in a room. I know who you are, and we can do targeted advertising. That's about it. There's a lot of subfields of artificial intelligence, including machine learning, reinforcement learning, planning. If you're curious about game playing, if you're curious about any of those areas, I'm happy to talk about them. My main focus today, and the main focus of most engineers, I think, in big data, is machine learning, though. So the ability to do pattern recognition on data and not have to hard code all the different patterns available in a program, right? So, if I'm trying to identify whether a user is going to churn or not, so the user signs up on your site and they disappear after 2 months, I want to be able to predict that with a probability. Machine learning is all about statistics and probability, with a little of engineering in there to work on bigger problems. And typically, machine learning is all about bigger data sets. So we see Hadoop, Spark, Flink, right? So these distributed runtimes, right? So you see all these number crunching frameworks. We started with Hadoop. Hadoop gave us the distributed system. And then we moved over to Spark. It's like, hey, there's this in-memory thing, and I can count things with it. RDDs are a really fancy counting mechanism, right? And then from there you can store all sorts of kinds of data in there. And then Flink is another version of this. The trend here is that we're going to see MapReduce engines become faster and faster over time. Whether Spark is the end-all be-all, I don't know. Will Spark be around in 5 to 10 years? Probably. Who knows? It's kind of like you can't predict where this is going to go. All we know is that these systems are going to get faster and faster and more resilient. Hadoop's been around for a long time. Spark's been around for 5 years by itself. And it's been built on this idea that, MapReduce came out of Google. We had Google File System and the ability to solve what are called web scale problems, right? So web scale is not MongoDB. Web scale is a real term where, you actually have to think about how do I store the web? That's a unique problem. That's not your MySQL database where I have a user ID and they signed up on this date and maybe they pinned these tags on Pinterest or whatever, right? It's not that. It's not so, it can be, maybe it's social graphs. That's sort of the new, we've had talks on graph analytics at this conference. That's sort of another sort of like web scale problem, right? Where you're counting connections to other people and that kind of stuff. Either way, number crunching engines need to get faster, and they're going to become more ubiquitous over time. Spark made it easy. We went from MapReduce, brittle Java programs, to functional programming, RDDs, statistics, and higher level primitives. And, so RDDs are the kind of like higher level primitives now. Now it's data frames, so now we're getting even higher, right? Data frames obviously came from R and Python. That's how statisticians think. But now engineers are starting to use this, right? So that's kind of where we're at now. So we have these MapReduce frameworks. We have some stuff written on JVM. We have some stuff written in Scala. It's all resilient now. But now, where do we go from here, though? So machine learning itself, it solves all sorts of problems. Everybody has their own machine learning framework, MLlib, Mahout, that kind of stuff, right? Machine learning is being used in all sorts of applications. Spam classification. So Google protects your inbox. That's a binary classification problem. So you label mail as spam or not spam. You build a basic bag of words classifier, right? Bag of words is basically where you take the count of all the words in the document, and each row or each column in a vector in a bag of words is a word, or the count of the word, right? And then you can take that and actually throw it into a machine learning algorithm. And then you can say yes or no. Yes, this is spam, this isn't spam. Another one of those, summarization. So this may not be a typical problem you think about, but summarization is actually taking the ability to digest a document based on what are the most important phrases in this whole article. So basically, too long, don't read, right? Machines can do too long, don't read. Face detection. So face detection is literally processing raw images, right? I take a picture of this room, and I'm going to count how many people are at this conference. How many people are listening to me right now? And if maybe if you registered your face with TypeSafe, I'd actually be able to tell who didn't attend my talk. Who are you? Right? So it comes down to the fact that, you have some analytics you want to do, and you're trying to do some sort of identification. Now we're getting into the Minority Report a little bit. Now we got eye tracking, right? So, like if you actually have a camera and you think about the Kinect, if you want to think about something a little more tangible. But, it's literally tracking motion, right? What can we do with that? We can actually figure out that based on the fact that your eye's dilated, you're more likely to interact with my software or with whatever I'm doing. That gives me a better user experience because I'm more excited, right? So machine learning is all about taking and extracting signal from data. And it might not necessarily be just your MySQL database for your website. It actually might be something a little more. A lot of the things I'm talking about are unstructured data. So unstructured data is a lot of what we can't process today. Spark and Hadoop and a lot of these other frameworks are good at spreadsheets. Spreadsheets are just what you think about. They're tables with individual columns. We have sc.parallelize. We can ingest CSVs really well, right? But at the end of the day, a lot of things are binary. Raw MP3s, images, text, Internet of Things. So you're like, wait, where did that come from? Sensors, all unstructured raw data where we need to think about them differently. I don't want to think about spreadsheets. I want to think about raw bits that users generate. My phone, over the next 5 years, is going to generate more data than probably we have in the last 10 years for all the internet. Because a lot of sensors are going to be like motion, tracking when I move, tracking when I sleep, smart homes. A lot of these things that are going to be up and coming in the next 5 to 10 years. We're going to need to be able to crunch that kind of data. The JVM will be the way to do that. But how are we going to keep up though? And how does this relate to you, the normal Scala developer? So it comes down to the fact that we have machine learning now. We have distributed machine learning. If you've ever seen MLlib, you've seen Mahout, you've seen a lot of the different machine learning libraries out there. But right now, it's all simpler models based on usually databases. A lot of it is baseline simple problems. Most of the industry right now, though, barely understands what logistic regression means. Logistic regression is just a two-class classifier with some weights. If you don't even know what a coefficient is, like, don't worry about it. That's most people. That's not applicable for a lot of software engineers. A lot of software engineers are focused on how do I build scalable systems? How do I make sure this stuff doesn't break so I can go to sleep at night? How do I build robust code bases? How do I build scalable systems, right? You're not necessarily worried about, machine learning, counting things and all this. Actually, what's cool though, machine learning is actually among the most hard problems for scale. If you want hard, machine learning is the way to go. So, but right now, especially in a lot of machine learning libraries, you only have binary classification. Binary classification covers a lot of problems. Fraud, anomaly detection, is it or is it not, right? And there's a lot of things you can do with just binary. That's not, I think a lot of problems are going to become what are called multinomial. Multinomial is the ability to have greater than 2 labels. So a multinomial problem is there's one of 2 billion possible people or more, right? That's a multinomial problem. There's lots of ML frameworks on the JVM though. We've seen Mahout, we've seen MLlib, we've seen R in the JVM. Weka is a great GUI, right? That Weka is written in Java. That was about, that's been around for a long time now. But a lot of this stuff is either academic or is a part-time endeavor. Nobody thinks about, okay, how do I actually build a separation of concerns with these things? Machine learning actually has a lot of components that a lot of people don't think about. Spark has estimators now. In Spark 1.4, they're trying to improve the ML pipelines. They're trying to make this a distinct thing. When in reality, while this is great and it's moving towards the right direction, it should be modular, right? So, and it's brittle. We can go the other side and say there's machine learning GUIs, prediction.io and COG, right? All Java-based again. But, then there's a problem of customization. How do I get my insights out? How do I get the attributes of my model out? How do I build a customizable model? How do I add new algorithms? There's a good middle ground here that hasn't been struck, I don't think, yet. So right now, problems. They're what I like to call monolithic. This is going to ring a bell for a lot of you who have dealt with microservices. So they bake in all the assumptions. Sometimes they can be harder to use and get started with. Like I said, MLlib has made this a lot easier, I think. You just do logistic regression.train and you got your model, right? That's getting there. But they're still not quite there yet, I don't think, in terms of how you use them, how you customize them. And again, no separation of concerns. Do we want to build web apps like that? Or do we want to be able to actually separate out what are the different concerns, like data ingestion and a lot of these other things that we typically don't think about as data scientists? So in this case, there's different concerns. Data pipelines and vectorization. So as I mentioned, Spark right now assumes that you just give them the data. But somehow that data had to end up in S3. That data had to be stored somewhere. That's an engineering concern. Your Akka actors, those are actually submitting something to a database. They're submitting something to an S3 bucket. They're submitting something to somewhere, HDFS, doesn't matter. Key point here, data pipelines. Now, how do I take that data and turn it into what's called a vector? A list of numbers that a machine learning algorithm will understand. That whole process is by itself a hard problem. Typically code is one-off scripts in R that's not reusable. When in reality, that's not the way to go. Every time you need to touch it again, every time you need to update your assumption about your model, every time you need a prototype, it's harder. Because if you think about it for a second, you don't build your software like that. You make sure it's modular, you make sure it's clean. If you want to build a real-time pipeline, a great example of this would be anytime you have one of your microservices where you submit an order or something, right? And it goes through the order processing system. You want that to be scalable. That ends up in your database. So that whole process can also be applied for machine learning, where instead of submitting it to my database, what I get out is actually several microservices talking together to form a feature vector. A feature vector is, in machine learning, just a list of numbers. It's attributes. So if you think about housing prices, right? What is the price of a house? If I'm trying to predict that, what are the attributes that are involved there? Could be the number of rooms, number of bathrooms, number of beds. How many master bedrooms there are, right? Who knows? The whole point here is that each item in a feature vector is an attribute. And we're trying to predict something based on that attribute. We're going to load that data from different sources. If we're working, especially with unstructured data, and that's kind of the key hint here, is that unstructured data is going to become more common here in the next few years. And we need to be able to build more robust pipelines to work with unstructured data. Unstructured data is images, text, audio. Those are raw files. Those are files coming from my phone that get submitted to your Akka web service, right? Scoring. How do I evaluate my model, right? So if you think about it, if I'm going to recommend you something, I need to be able to say, well, yes or no. This did good, this did bad. You need to be able to score a model. You need to be able to evaluate them. Algorithms should also be self-tuning. So I should actually be able to, at runtime, evaluate a model and actually update my assumptions about the world. Bayesian updates. Bayesian is just basically where I have an assumption about the world, and I'm going to increment rather than traditional statistics where you count things and then you have like a minimum count before it's valid. In this case, the null hypothesis versus not. In this case, this is another form of A/B testing where you say, okay, now I know this much about the world. All right, now let me update my assumptions. Okay, this happened, let me update my assumptions. That's more or less how the real world works. That's Bayesian statistics. I want to be able to evaluate these things. Model training. So this is the scaling part that you guys haven't seen a lot about yet. So in this case, when you're building out an ML pipeline and you have 100 million examples, that won't be unrealistic. Do you want that to take a day? A week? Do you want that to be brittle? If you want to build a real-time streaming system, streaming machine learning is, again, where things are going. If you're going to want to build that, you're going to want to be able to build the data pipelines in isolation and test them. That's a software engineering concern. You're going to be able to evaluate your model in isolation. That's again, another concern. So right now, machine learning frameworks are monolithic. They don't allow you to test things in isolation. You should have more control over that. I should be able to scale model training independent of anything I'm doing right now. Again, SparkML is doing this right. Right now, they give you the ability to inject your own models, right? And you can scale them independently. So you can build them on top of Spark. And then from there, all you need to do is implement the proper interfaces. And you'll integrate right into the Spark runtime natively. So they're getting there. So other than that, so what I'm getting at here, current frameworks are monolithic. And the trend, even in Spark, is to move towards microservices. Micro models, micro pipelines, right? So the ability to actually take and test individual components of a machine learning pipeline. What if I want to change my model? That should be replaceable. Everything should be replaceable. Everything should be updatable. These are all software engineering concerns. That's not something you've typically thought about probably when you're dealing with data. So the basic idea would be to take abstract concepts and reduce lock-in. Math is just matrices. I shouldn't have to think about, well, how do I do math on Spark? How do I do math on Mahout? How do I do math? It's all the same. That's silly. Math should be cross-platform. Data cleaning should be cross-platform. Data cleaning, I should be able to inject that into the distributed runtime. I should be able to clean my data independent of format on HDFS, in S3, what have you. Model training, that should be independent. I should be able to run on Spark or any kind of chip. So what I'm going to mainly talk about today from here on out are parametric models. Parametric models are matrices. This is recommendation engines, this is neural networks, this is regression. A lot of baseline parametric models cover, I'd say, most machine learning problems. There's other non-parametric models. Random forest is a great example of this, which still involves feature vectors. But from here, I think the hard part of matrices, or the hard part of machine learning systems that have not been solved yet, is actually making matrices work really well. In this case, especially ND arrays. So ND arrays are a strange concept for a lot of people. You see them in MATLAB, you see them in R, you see them in Python. You have sort of tensors in Scala. When in reality, like, an ND array is actually just a linear buffer with basically an interpretation of the data. If you think about how you arrange just a row vector versus a column vector, it's still the same length, right? All I did was swap. This is the cool part. All I did was, if I have rows by columns, if I swap columns by rows, I didn't actually have to move the data around. I just changed my interpretation of the data. You can actually build something, you can actually build 3 and 4D and 5D data structures with just this basic idea. All you do is change the interpretation of the data. No framework has done this well. So we have tensors. People have built dedicated tensors. But if I'm going to be solving more advanced problems later on, I'm going to need something that's I don't want 4D tensor. I just want ND array. I want something simple. The other languages have done this right for a long time. I think it's about time we modernize this a bit. So just to be clear, so if you guys haven't seen tensors before, think of it as two 2x2 matrices. It's a 2x2x2. So if you want to think about 3D, think about images. Images have an R, a G, and a B. And I have a pixel each channel. Each matrix is part of a channel. That's a 2x2 image. A 2x2 image is actually 3D when it's represented in data. So there's your baseline example of a tensor. What we typically do with images is we scale them down. When you have grayscale images, you take away one channel and you're left with just a matrix. I mean, so at the end of the day, like tensors are already pretty common, and I think that they're still not done the right way. When the most basic languages have already gotten this right. Languages for normal engineers, normal scientists, they needed this a long time ago, so they built it themselves. The problem, though, is those systems don't scale. And typically, ND arrays are involved with bad engineering. I think we should fix this, right? So how do we do that? So first of all, as engineers, we need to worry about chips. You're like, wait, what? So CPUs. So everything runs on CPUs today. What you're going to find, though, is that GPGPU is starting to become more common. So GPGPU stands for General Purpose Graphics Programming, right? So General Purpose Graphics Processing Unit. So I just call it General Purpose Graphics Programming, right? So that's the ability to use your graphics card to do programming. You're like, well, what's that for? Matrices. Your screen is rendered by something that knows how to calculate things really well. Like, it knows how to take blocks of numbers and manipulate them. And it knows how to do it in parallel. So NVIDIA cards have thousands of cores in them. They're dumb. You can't do a lot with them. They're not quite general purpose yet. They're a lot harder to program for. And this hasn't been immediately accessible from Scala, I don't think, yet. It's getting there. We got Breeze. We got some other libraries like that. Breeze, I think, is still stuck on CUDA 5.5, though. We're on 7. I don't know about that, but key point here. The ability to optimize on a per-chip level. So something beyond GPUs now, FPGAs. Being able to customize circuits, and then from there, being able to program them. Scala and OpenCL will actually allow us access to FPGAs from the same standard. This is actually more accessible than you realize. If you have any sort of numerical processing you're doing, being able to optimize at not only scaling out to a cluster, but then relative to the configuration of your cluster, CPU or GPU, mixed possibly. Maybe you're experimenting and you want to try a few machines with CPU and a few with GPU. Maybe you just want to add a few incremental updates to your cluster. We should have the ability to do that. The JVM is already the best system out there for scaling systems. It just works, right? We got HDFS, we got actor systems, we have the ability to do all sorts of multi-threading. Akka blows up my box every time, right? It's like it uses every core. It saturates it. We're still not there. We can actually go a step beyond this now. We can actually do processing on different kinds of chips. So I want to be able to use Akka from a multi-threaded system, but still have access to faster numerical computing. That's where things are going. The ability to actually run things on different chips. Yes, there's some C involved here, but Java's written in C++. You as a Scala engineer shouldn't have to touch that. Robust systems are written in Scala. But we shouldn't be oblivious to the hardware, though. We should know what's going on. So the problem with a lot of current matrix libraries is a lot of this stuff is a secondary concern. Yes, I want it to be cross-platform, but I don't want to lose the ability to optimize on a per-chip level if I have access to the right abstractions. This is a lot of what Python does well, but it still forces you to drop down to C. We should be able to have transparent access to different kinds of chips. There's no reason we can't do this with just basic JNI. So the ability to access so the ability to scale out in a cluster on the JVM, which we already have the ability to do, but then deploy mixed chip clusters and get access to faster numerical computing. So again, I'm talking about the future. A lot of you guys are probably just writing web applications right now. I think machine learning in the next few years is actually going to become more of a concern. Data-driven apps, sensors, we're going to need faster numerical computing. So in this case, why CPU versus GPU? Look at the differences. I mean, they speak for themselves. This is execution time per second with CPU versus GPU. GPU is 1,000 times faster on a lot of basic problems. They have their trade-offs. So, right now, like, there's libraries that are accessible. BidMock, JCUDA, if you want to work with some GPUs. Problem here, though, is they aren't good for all workloads. So one of the problems with GPUs that still has to be solved transparently is the ability to upload data. The GPU is literally a server. So when I called it a dumb chip earlier, it's because the CPU controls it. The CPU tells the GPU what to do. So the GPU is great at one thing, numerical computing, and rendering things. Rendering things is all matrices, right? So basically, what you have to do with GPUs is you have to evaluate what kind of problem is this. Is it greater than linear? If so, I can upload the data and it'll be worth it. Otherwise, it might not necessarily be worth it. It depends. It really just depends on the problem at hand. Either way, you need to basically treat the GPU as a server. So your best bet are going to be mixed CPU GPU clusters. Again, we have CPU clusters already. We can deploy boxes in AWS now. So we have the reason Amazon actually invested in GPU infrastructure was because this is actually becoming more. GPUs are becoming commodity. They're becoming more widespread. So if you're doing numerical computing, it's something to think about. So data pipelines. So my other concern here. More data will be binary. Sensors, images, media will become more commonplace. We need to be able to deal with images. We need to be able to deal with text. We need to be able to deal with a lot of these automatic pattern recognition systems. If we're going to do a lot of the streaming machine learning that people are all clamoring about in Spark streaming, for example, we're going to need to step it up on the data side. Again, we're getting a lot of the basics right, and it's still very early. What I'd like to say now, though, is I think we can go a step beyond this. If we want to do face recognition and other kinds of cooler problems, we're going to need to work on different kinds of data. So beyond that, so this comes down to dedicated libraries. The ability to actually think about, okay, now I want a dedicated library for vectorization. I want a numerical computing library that's cross-platform. Right? I don't want all this stuff tied together because if I'm going to run numerical applications, I want to be able to scale that out as an individual component. So if I'm working on something besides machine learning, I want to be able to use vectors in other applications. Isolation of concerns. Other than that, again a great example of this is Internet of Things. I think people are probably underestimating sensor data here, but the ability to actually think about, well, okay, so my fridge is connecting to Akka, and it's telling me when I should wake up, or the possibilities are there. I mean, it's going to take time. A lot of this stuff is the future. But the key thing here is the JVM has the infrastructure to do this. We just need to extend it. So other than that, I'll go into some a little more technical details now for those of you who haven't seen a lot of machine learning before. So scoring, another concern I talked about before. Area under the curve. So area under the curve is actually the ability to say, should I say yes or no? So what is the likelihood that something is spam? Should it be 70% as a threshold or 60? Right? So the ability to actually evaluate trade-offs in a model. That's why binary classification is actually special. F1 score, the harmonic mean. The ability to evaluate multimodal, so multi-label models, right? Greater than 2. So it's the ability to actually assess the trade-offs of accuracy. So true versus false. Different loss functions. So different loss functions. This is parametric model specific. But if you've ever seen a regression problem, you're optimizing something called root mean squared error. There's other kinds of objectives. So you can actually tell a model like what to optimize, right? Hyperparameter optimization. So lastly with scoring, the ability to actually self-tune a model. Other than that, again, these should be embeddable. So these shouldn't be tied to a particular system. Right now, everybody has their own interpretation of how this should work. But if I have, let's just say MLlib, right? They're using Breeze underneath, but Breeze makes some assumptions. JBoss makes some assumptions. You know, and that shouldn't be the case. I should be able to plug that in. I should be able to tell Spark, use CUDA. Spark, use FPGAs, right? So the ability to actually pick what numerical library I want to use. Data pipelines. I should be able to tell Spark how to do the ingestion, right? Finally, training. If you guys haven't seen machine learning before, the basic ideas: split train test. The ability to take a model and say, train on this data, evaluate on this data. How well did my model do? So right now, typically data scientists sample data. So they say, let me train on 100 examples, and then from there, I'll figure out, okay, now, based on that, I can say how well my model did, how well it will generalize. At scale, eventually we'll be able to train on all the data. Or be able to do train test split on 100 million examples, or whatever is sitting in my database. If we have legit data pipelines with real-time streaming and whatever else built into it, that shouldn't be intractable. So this brings me to deep learning. So deep learning is something you've probably seen a lot about. You've seen it breaking records, right? A lot of it's done in Python, though. The normal training time right now, and people are happy with this, it takes hours, weeks, days. So a lot of work is being done in HPC, high performance computing. That's the old school way of doing it. That's model parallelism. NVIDIA is spearheading this right now, where the ability to share data between GPUs. The ability to take data and shard a model and actually shard it across multiple GPUs. Disbelief. So a great example of scaling out on just multiple cores and doing parameter averaging is Disbelief. This comes out of Google. What they do is they actually take a data set and partition it. And they say, based on this partition, so partitions probably sound familiar to those of you who've done Spark. So partitioning is actually taking data and saying, okay, these 10 examples are going to go on this core, these 10 examples are going to go on this core, and then imagine scaling that out horizontally and vertically. And then what you have is you actually have something that averages the parameters. So you have something that's aware of where the data went and why. This is very similar to like a named node in HDFS. And then what it does is it keeps track of it. Basically what happens is after you get that model partition, it pings the data back up to the server. That's called a parameter server. So what it does is it updates things. So there's a few ways to scale out deep learning now. So deep learning is good at one thing primarily, unstructured data. So that's kind of what I was getting at here: images, text, and audio, and also like Internet of Things. So the problem with data science right now is we have to come up with what the best features are, right? So I have to think about, well, this correlated with this, and that means this. Feature engineering is most of a data scientist's job. There's people who just do modeling. Deep learning, what's great about it is it's more of an engineering problem. It's more of a scaling issue. Deep learning's actually default mentality is throw hardware at it. Throw chips at it. That's what you do. That's actually what kind of makes us fun about with the JVM, is because that's our mentality as well. Scale. Throw CPUs at it. Throw hardware at it, right? We already have the ability to do this. So deep learning is great at automatically recognizing faces. So a neural network, when I showed it just images, actually produced these faces automatically. All it did was it said, let me look at these faces. Cool. Okay, I know what a face is now. Each of these is a neuron in a neural network. So yes, this is the unsupervised feature learning, if you've ever seen that. So unsupervised feature learning, if you saw the Andrew Ng story a few years back in the New York Times, where it watched YouTube videos and automatically learned how to detect a cat. This is that same thing. This is accessible now. automatic pattern recognition. So again, primarily for unstructured data. Another great example of this. This is a word cloud where actually all these words are topics. The rendering algorithm here is called TSNE, T-stochastic neighbor embedding. These are actually, each of these words is actually represented by a vector. And what you're going to find is that there's actually clusters of 2, 3, 4, 5 Spanish words. It automatically figures these things out based on word usage. Neural networks can actually learn word contexts. This is an algorithm called Word2Vec. If you guys have ever, if you want to Google something, Word2Vec is in Spark now and you can use it. So Scala, it comes down to the fact that we have the JVM, we have a real-time framework for processing data already, we already have the ability to create composable data pipelines with actors. Functional programming maps really well onto these paradigms. Map and reduce, take some data, crunch it, transform it in a way, turn it into vectors, do the number crunching. You know, then we have key value stores. So one of the things Spark has not solved yet, distributed matrices. Yahoo actually uses a framework called Pistachio. It's a key value store written in Java. Yes, Java, unfortunately. And what they actually did was they actually wrote something that this powers their ad network. They actually have billion link matrices powered by this. It's distributed matrices. So a distributed key value store. Java has great potential for this. So they actually built a parameter server in Word2Vec. I'm actually working on integrating it into my framework now. So I'm working with the Yahoo team on this. Either way, the JVM has the ability to scale, and it's great at number crunching. So the way we learn now, again, monolithic frameworks. So everything makes assumptions. No per chip optimizations. I should be able to tell it what chip to use. No tensors. It's 2015. There's been a lot of work being done, but tensors are still not very commonplace. This needs to change. Isolation and less lock-in. So we need the ability. So just like we have microservices now, I think we're going to see a trend over the next few years where data pipelines are going to be considered apps, and those are going to be closer to the revenue because data-driven apps are going to be the way to go in the next few years. Basic machine learning, I think, is going to actually be a key characteristic in engineers' tool belt. This should be easier to do, though. The JVM is a way to make it happen. Other than that, other links. This is my take on it. All these things are swappable. Happy to answer questions now. Thank you. Okay. If not, go ahead and, yeah, thanks.
One thing you haven't mentioned anything about memory allocation. One of the things in engineering, these big data applications often run into issues with garbage collection. So do you see sort of extensions to JVM being important here and that sort of thing?
So I got that covered too. So I actually use Netty for that. So I actually use off-heap byte buffers for that. The JVM. So when I allocate things natively, you can actually release them. So I use Java's auto-closable routine for that, like the interface. So I use what's built tri-finally for that, if you're going to allocate native resources. All right. I think you guys want to get to your real talks. Go have a good time. Thanks.